as well as professor in chemical and biological engineering. Really delighted to introduce Aloy here, and I cannot top Josephine's introduction, so I'm just going to fall back on the engineering introduction. But Aloy originally comes from Brazil, and it was, I guess, Milan, Boucham, myself, the summer of 2022, when we started to work for the transdisciplinary collaborative PhD project. He was one of the 6 students who was chosen out of 140 applicants across UBC to work with us in sort of imagining what might that look like. 4 years, I guess 3 years later, we have 4 transdisciplinary collaborative PhD students who resides in IRES here, so you'll be hearing about them later on. And you finished your first degree in electrical engineering and now a master in IRES. Connor McLucan, Wushango Poloni, and I have the privilege of working with you and in your project, which you'll talk about.
Thank you. Thank you. Yeah, glad to be here. Glad to see familiar faces. Presenting to friends is definitely different than strangers, and that's good. So today I'll be talking about using artificial intelligence for targeting energy transition policies. Maybe I'm too far from the thing. Okay, let's go back. So I'd like to start with the land acknowledgements. We are located in the traditional, ancestral, and unceded territories of the Musqueam, Tsleil-Waututh, and Squamish nations. I'm privileged to live in this land. This is the view from where I live. Yeah, I'm very privileged. And so I have always mixed feelings because I can enjoy this, but also, yeah, the past, the fact that this land has been stolen always makes me also, yeah, reflect how life can be good and bad at the same time. I am grateful also for the partnership with other universities through ACET. So ACET is an initiative based in UVic called Accelerating Community Energy Transformation. And it's funded by the Canada First Research Excellence Fund. And okay, so let's start. So is energy in British Columbia clean? Maybe. A lot of people, when I talk to them, tend to think yes, because they're probably thinking of hydropower. So they're thinking of electricity. But when you think about the rest of the energy system, when you think about transportation, don't have to press that button. When you think about transportation, when you think about residences, when you think about industry, a lot of it still comes from fossil fuels. So overall, energy in British Columbia is not very clean. So you might think, no problem, we can just switch technologies, right? Let's start using electric vehicles instead of gasoline vehicles. Let's start using natural gas. Let's start using heat pumps instead of natural gas furnaces to heat our homes. And let's switch all natural gas furnaces in the industry to electric arc furnaces, to electric generators, and so on. But it's not that simple. In California, they tried to incentivize the adoption of electric vehicles with a policy that was universal. Anyone could have access to a rebate. And so what happened? Most people who had the highest income, you can see that in the darker regions, also had the most rebate. So the rebates were allocated to regions that already had more income in the first place. Okay, so British Columbia has a policy for targeting heat pump rebates at northern communities. And they also have a pretty simplistic way of targeting. They just use latitude. If you're above a latitude, a certain threshold, you get the rebate, otherwise you don't. So this is regardless of home value or income level. So perhaps this might also start creating disparities here. So why should we target or differentiate our policies instead of creating universal policies? For equity reasons, because people have different needs. For justice reasons, some people deserve more something than others. And also for budget constraints. If you had the money, perhaps you could spend it on the whole population, but sometimes policymakers don't have that privilege. Okay, so let's suppose we want to increase heat pump adoption in British Columbia. We want to switch natural gas furnaces to heat pumps. How do we go about doing that? how are we going to basically differentiate our policies so they're more holistic instead of using these basic thresholds? In other words, which population features like income levels, education levels, latitude, greenhouse gas emissions, so on and so forth, would we use to differentiate who gets access to our rebate? Or perhaps if we want to create a mandate, who's targeted by the mandate? And given one feature, where do you draw the line between who is eligible and not for our rebate? Especially when multiple features matter at the same time. So suppose you pick income as your feature. At what income level would you say you're going to get this rebate? And below that income level, you will not. Okay, so let's go through some of the features that I picked for my research. So I looked at income and housing quality, and I used the Community Wellbeing Index from Statistics Canada. Since the quality of your home might determine your ability to install new equipment, how much you are and will also like influence if you're able to purchase equipment in the first place. I looked at latitude, because latitude correlates with how much heating you need. That's why the province was using that latitude threshold. This is the threshold the policy is using. So it crosses a 100-mile house. So everyone above this can get the rebate. So the northern you are, the more heating you need. So maybe that latitude is also important to look at. I consider education levels and labor force participation. And I also use the Community Wellbeing Index from Statistics Canada to get this information. Because I reasoned that if you have people who can install the heat pumps, like electricians, engineers, and also urban planners, and people who can plan the energy system to install these, it might be more likely that you're going to be able to transition these energy systems. And I also looked at natural gas consumption levels. So if you want to reach climate goals faster, perhaps you'd like to target places that have the highest natural gas consumption first. And I also looked at local government climate action plans. And I used the survey results from something called LGCAP, a local government climate action plan survey, which asked municipalities around BC if they had a climate action plan. If they didn't, why not? What barriers did they face in implementing climate action? And what I did was aggregate that survey numerically. So I created two aggregate variables. One is a climate plan variable that combined if they have a climate action plan or not, if they declared a climate emergency, if they have reports on corporate emissions, if they have a net zero or carbon neutral target, and a community greenhouse gas tracking. And I also created a number of climate action barriers aggregate variable, where in the survey, they say, do they have staff capacity for greenhouse gas emissions tracking or financial capacity, and so on and so forth. I also looked at population and remoteness levels, because if you have a higher populated area, you might have more access to the people you need to install these equipments. So when you search on Google for electricians in Vancouver, you have a variety of services you can reach. But if you look at Tassis, for example, a municipality that's very, very small, if you search for electricians, you don't find anything. So the closest larger municipality from Tassis is Campos River, 2 hours and 40 minutes away. So you can imagine if you are remote, that might also affect your ability to install new equipment. So I used the remoteness index and population levels from Statistics Canada also in that data. Okay, so we looked through many different variables, but then you have to make a decision. Where are you going to draw the line to separate who gets your rebate and who doesn't? So if you look at latitude, where would you draw the line? This is the statistical distribution of latitude, of municipal latitudes in BC. The higher the bars, mean more municipalities fall in that region. So most places are in this latitude. You can see this is not really like a normal distribution. It looks like there's two modes. So perhaps you could draw a line to separate latitude right here. This is where the government has drawn the line to separate the northern heat pump rebate. So perhaps people who are below the line don't get the rebate, people who are above the line get the rebate. But what happens when you're looking at multiple features at the same time? If you're looking at latitude together with income, together with education, because you want to look at more holistic policymaking, how would you start drawing boundaries to separate groups? You could try to draw a plane and separate based on latitude, since this seems like it's a dominating feature separating two subgroups. And then finding where to draw the boundary in the other dimensions is more difficult. And if you have more and more features, and suppose you separate each feature into two subgroups, like an income, with income, you separate a low income group, a high income group, with education to a low education, high education group. and so on and so forth, you increasingly you have an exponentially growing number of possible groups. You would have 16 possible groups just with these 4 features. Okay, so if we use 10 features, suppose, and split each feature into 2 subgroups, we could have more potential subgroups than the number of municipalities in British Columbia. So what hope do we have to identify typologies of municipalities using more than 4 features? Okay, so to what extent can artificial intelligence help policymakers identifying these typologies to target energy transition policies? My methodology is starting with selecting the relevant features that we want that are relevant for policymaking, things like education, income, electricity use, remoteness, and so on. And then the algorithm I use, I say AI, most people nowadays, AI has become a buzzword, so most people are thinking of large language models, but I'm using statistical methods that are decades old. So this principal component analysis and k-means for clustering and reducing the dimensionality of my data. And I'll explain how they work in a second. And once you apply these, you have your clusters and you can characterize them. So for example, one cluster might be higher income, higher electricity use, urban communities. Another cluster might be medium income, medium electricity use in urban communities, and so on and so forth. And afterwards, you can map where they're located to start making policies. Okay, so the data, this is a summary of the data used and the method. The emissions data comes from the community energy and emissions inventory. And I have data for residences, transport, and industry. Today, I'll just be exploring the residential sector. So we're talking about heat pumps, but we can also do a similar analysis for transportation and industry. We have latitude and longitude. We have the community well-being index, population size, remoteness index, and the local government climate action plan results, survey results. And the method involved a few months to, first of all, identify all these relevant data sets, and then cleaning, harmonizing, and merging them took another couple of months. And then after that, I had to engineer new features. So for example, calculating energy per capita. So I had energy from one data set, population from the other, and then dividing both together was a new feature, energy per capita. And then reasoning which features would be most relevant for policy targeting and applying the algorithm for clustering were the steps I took. Okay, so I'll quickly explain what the method looks like. So principal component analysis, or PCA, is like projecting something on the screen. So I'm a 3D object. My hand is 3D. If you project it on the screen, it becomes 2 dimensions. But yeah, you can still see it's a hand. So you reduce the number of dimensions. You reduce some information, but you can still retain the most essential information in your data. So again, if we have multiple dimensions, you can reduce that to less. So like from 3D, you can go to 2D, but also from like 10 dimensions, you can go to also 2 dimensions. Secondly, once you have reduced the dimensionality, I applied k-means for clustering. So with k-means, you can tell the algorithm how many clusters you like to find in your data. So here, we might have told, look for 3 clusters, and it will group your data points based on similarity and based on how close they are together, basically. Okay, so let's go back to that question. We want to increase heat pump adoption in BC, right? Switching natural gas furnaces to heat pumps. How do we determine who's targeted by our policies? Let's look at using this tool for designing holistic heat pump policies. So if we apply principal component analysis on the 18 features that I think are relevant for residential heat pumps, so we have a lot of them: latitude, income, housing, education, labor force participation, population, remoteness, a lot. So that would be a lot to wrap your head around. And you apply principal component analysis. Principal component analysis will reduce all of these to less components. So we have here the 4 components. We have 18, what you start with, and 4, what you might end up with. So you reduce the number of dimensions. And then each component might load a feature more. So here is the highest loading. So for the first component, latitude loads it heavily with remoteness. For the second component, the emissions factors and energy per capita loads it heavily. So you can basically characterize what these components mean by looking at this kind of graph, because it seems very abstract to say what's a principal component 1 and 2, so on. So this kind of graph tells you what they're basically characterizing. And then we can apply clustering, and the optimal number of clusters when you're optimizing by the silhouette score, which measures how tight the clusters are and how far apart they are from each other. the optimal number of clusters was 2. You can also plot the number of clusters versus the the cluster quality score. There's multiple ways to measure cluster quality. One of them is a gap statistic. I don't think we'll get into that. We can talk about it later if you want. Another one is the silhouette score. So you plot what's the best cluster by looking at number of clusters versus the score, and then you can pick perhaps number 2. So that'll be the optimal number of clusters. Okay, so this is how the map looks like when we let the algorithm optimize by itself the number of clusters. You can see cluster 0 spread throughout the whole province from the north to the south, but most of them are on the north. Cluster 1 is more concentrated on the south. There are some on the north, but less. If we compare this clustering with the existing policy, you can see this is the current policy. If we only cluster on latitude, it's actually funny because the algorithm ends up giving results that are basically identical to the existing policy. So if I run my algorithm with only latitude as a feature, the clusters that emerge are basically what the government has already done. When I add all of these other features, so in total 18 different features, the clusters look pretty different from before because now these blue locations are also underneath. And why do they really characterize, right? So what's the blue locations? We can look at tables like this and calculate the average values for each cluster. So one cluster was higher latitude on average, lower income, lower housing quality, much lower education, lower labor force participation, lower population size, and then you can keep going to characterize your clusters. And just to give you a few examples, this is Fort St. John. So this is one of the clusters, and this was, I think, if we go back here, Fort St. John's around here. So that's the blue cluster. So Fort St. John has a population in the tens of thousands. It's very close to Site C Dam. You probably heard of this. And the economy is mostly based on resource extraction farming. But this same cluster also included an island called Aloy Bay. So you can see that there's a lot of diversity within these clusters. So Aloy Bay has less than 1,000 people. It used to be mostly a fishing community, and the population is currently aging. And so they're still deciding how to overcome that aging population. On the other hand, the other cluster includes more urban communities, but also some remote, relatively remote, like Bowen Island. Bowen Island is pretty close to Vancouver, so maybe we don't need to call that super remote, but it's still an island. So you can see the diversity of the clusters within both groups. And Vancouver, of course, is also in the same cluster as Bowen Island, because they have both these places have higher education, higher income levels. Okay, I think we won't have time for. Okay, yeah, it's fine. I think I don't need to go through the second exam. That's okay. I think this is good. Yeah, no problem.